Today's topic is about building other combinational gates, some of the simple gates. We look at inverters. So far we've been looking into inverter from different angles, from delay, from power, from noise margins. And now we will look into how we can build some other gates like NAND, NOR, and NOR type. A lot of things that I said in terms of propagation delay and power numbers, those are identical, whether it's a CMOS inverter or other gates, but there could be some unique things for these bigger gates, which I'm going to explain. So if you look at, the first thing to look at is, it's called CMOS. It's a complementary metal oxide semiconductor. The two important pieces it has are, as we talked so far, pull down and pull up. Okay, in pull down, as we have seen in the case of inverter, we have NMOS is used, which provides a path to ground, and then we have pull up, where we use PMOS. It provides a path to VDD. So in a simple inverter case, we put one PMOS connected to VDD. We connected this point together, and then the other side of the NMOS we connected to ground. You must be wondering why we didn't use, for example, NMOS to connect to VDD, or why we didn't use PMOS to connect to ground, right? So one of the main reason for that is that this node here, when NMOS is on, of course, when NMOS is on, this provides a short circuit, but already there is a small tiny resistance, which is the resistance that the channel offers to current. But this point here, the maximum voltage it can go to is VDD minus threshold voltage of NMOS. Okay, so let's put it here. Oops, not this one. So this point, the maximum voltage it can attain is that VDD minus VTN. So it will never go to this voltage. So if you can live with it, okay, but it's not a strong VDD. So PMOS, when they conduct, they provide here when they conduct it. Of course, there is some drop here. I'm just assuming there is no drop. So then they provide a VDD. You must be wondering why in NMOS case this point doesn't go beyond VDD minus VTN. So here is an important thing. So I'm explaining that. And remember that in the case of NMOS, the node which is at higher voltage is drain. We always look at drain in the case of NMOS, the one on this side. If we have, remember we had channel here, we have gate there, we drain, we source, we connect it. So the point, the node that is at higher potential, that is drain, and the node that is at lower potential, that is source. But in this case, this point right away we connect to VDD, even to start all the time. So this is drain. And this point, that where the voltage swings, so it sometimes goes lower and higher, this will be the source. So that is an important factor. So in order initially, we said gate to source voltage of an NMOS needs to be greater than VT. And so this one, this need to be greater than V threshold voltage. And this gate to source is the voltage at gate minus the voltage at source. So if you know that, okay, let's say before we turn on this to connect to VDD, okay, this would add 0 voltage. Okay, so gate to source voltage. Or think of that, we want to connect to VDD, this one has 0 voltage. So initially gate to source voltage, yes, whatever gate voltage we have here, that's fixed, right? We typically apply 1 for NMOS to conduct. But this, as we initially gate to source when it's 0, it will start conducting. So there will be current flow. it will go into well, drain to source is already higher, will go in a saturation mode. But the important thing is, as this is on and you're charging this capacitor, this represents whatever capacitance is at the output of inverter. This voltage will increase, and as this voltage increase, gate to source voltage will decrease because this is fixed. This is now going to increase, so the difference between them decreases. And at some point, when this voltage reaches to voltage VDD minus VT, right? Then this is at VDD. So VDD cancel, VTN is the net one. So when this point reaches to this voltage, and after that transistor is in cutoff region, is actually stopped. This is disconnected, and this voltage or this point, the last voltage that it gets the maximum charging was VDD minus VTN. So in other words, we can say that, okay, when you put NMOS here for the location of PMOS in order to connect to VDD, it's not a strong one. It's not a strong logic high. Means it's not a 100% VDD, or not as close as you get a PMOS. And NMOS, when they are used here on the pull down side, right? And they can really they can create a strong zero. When they conduct, they can really take this point to zero, not 0 plus VTN, which in the case of PMOS happens if you connect PMOS for the ground. Okay, hopefully that was clear. So let's make a different circuit, and we are making a NAND here. So what we do is, I was thinking of which way I go. Let's do this. A NAND is this, right? When you have 0 0, an AND case is 0 and 1, 0 1 1, 1 0 1, 1 1, then 0. Here is something important. A B, and this is A B. This is A B bar. So A and B. So when you connect two NMOS in the series way, they become like AND. Means the circuit, if this is a capacitance here, right? This one is better. If this node, let's say we don't have PMOS connected, this is where capacitance is. NMOS provide a path for the capacitance to ground. So unless we have both NMOS on, this signal will not go down. Okay, so when A is 1, B is 1, only then this node will go down. A1, B1, only this node go down. This is an inverting, right? So it's not like a B, it's not AND, it's NAND, because output gets NAND. If A is 1, this is on, but this AB is 0. I'm assuming I'm connecting A here and B here. In this case, when one of them is off, output is 1, mean it stay at higher voltage. I'm assuming it's previously charged. So you understand the difference? The important thing is that this is the reason why we call them complementary CMOS, that whatever is your pull down, the pull up complements it. So if this is your pull down, let's create a whole complement of this. This becomes A naught plus B naught. Remember some of the theorems we studied in the combinational circuit? So when you take a complement of this whole thing, because it's a complementary CMOS, you open it like the complement of first plus complement to the B. A plus B. This means A and B are in OR. Either this or this. I mean they are in parallel. And this complement on top of the indicate that is a PMOS. Right? This on input, let's say, let's look into this. Let's connect them. Let's make it a little bold. Okay, so this one is connected to VDD. So now look at when A is 0 or B is 0. This is A, this is B. Like this, the same A. So you can think of this is connected like this. A and B is connected there, and at the same time connected to, oops, like that. Okay. This way. Now look at this table. A is 0, B is 0. A is 0, B is 0. Both PMOS on, and there's a strong pull to connect this node to VDD, means high. When A is 0 or B is 0, one of them is on, and that is sufficient to connect this one to VDD. When A is 1, B is 1, we know that these one are off, this is on, and we have a ground path. So this is the only path when both A and B1 are pointers go by. You got it? In the same way, let's, I was thinking of doing it later on, but let's do it now. Yeah, okay, leave it like that. So we have NMOS here. What if we connect NMOS in parallel, and we have PMOS the other way around, right? What if we have this scenario? So we have this one, then this. So what do you think this one? Guess, please. Now either when this is 0 or this is 1 or this 1, this will be a path to ground. So let's create a truth table for this one. A, B, and this is our output. This is our output. Okay, let's all the combination. When A is 1, B is 1 or A is 1 or both of them 1, the output there will be path of discharging here, or through both of them. So that will be 0. When both A and B are 0, 0, this will be off, and both of these will be on. So that provides us 1. Do you remember which gate gives a functionality like this? Yes, you're right. It's NOR. NOR. So if you don't remember, OR is always whenever one of them is 1, output will be 1, both 0. And NOR is the opposite of. So this is how from the function you create pull up or pull down, and then you complement it to get the other side. Okay, hope that was clear. In the next video, we will look at some of the impact of how different, and we can have a different delay for different inputs, and we'll look into that in more detail in the next video. That's all for now. Thank you so much.